Hello everyone, this is Dr. C. Welcome to take 2 of the weak acid, weak base pre-lecture. So let's just get right at it. So we started to talk about weak acids, and what you'll notice is that the vast majority of acids are weak acids because for the most part we're just going to focus on 6 common strong acids. All right, so make sure you know that list of 6 common strong acids. There are more than that, but most acids are weak acids. So this is nitrous acid. This is a weak acid. And using the definition as it's shown in the book, the Bronsted definition, we would say an acid is a hydrogen ion donor. And another definition of an acid is acids produce hydronium, H3O+. So you do have to learn how to write out these equations. It's hard to solve a problem correctly with an ice table and solve for pH if you don't have the equation right. So when you're writing out the reaction of an acid and water, the acid donates an H+ to water, producing hydronium, and then you'll also get what is the conjugate base of that acid. Okay? When that acid loses that H+, what you're left with is what is called its conjugate base. It has one less H+ than the acid it came from. Now, as you probably already know, for strong acids we assume the reaction goes to completion. Weak acids do not go to completion. All species are present at equilibrium. That is why we are going to have to set up an ice table to solve for the pH of a weak acid. And typically the equilibrium lies far to the left. Typically, 99% stays as the weak acid and only 1% ionizes, goes to product. Now again, that's just an estimate. It depends on the weak acid. It depends on the concentration of the weak acid. All right. Now, I'm sure you can write the equilibrium constant expression for that equilibrium up there. Don't include pure liquids. We'll come back to that in just a minute, but I want to again re-emphasize the difference between a strong acid and a weak acid in terms of ionization. So this is a nice graph to look at. Now, these acids are not laughing at you. Ha ha ha. Oh, that was not very funny. But what this is representing, and we'll use this a lot, HA stands for some generic acid. Okay, H+, and then the anion, whatever that happens to be. It's going to vary depending on the acid. Now, normally we would write that in water, producing H3O+, and the conjugate base A-. Now, you will see this, and I'm going to write this like this. I don't like it. It's really not showing it as an acid-base reaction. It's just showing the acid ionizing and breaking apart. But just to show you, you will see this. I don't like it. The acid just breaking apart to H+ and A- in solution. Okay, so that's why I say sometimes we will use H+ as shorthand for H3O+, but I prefer that you write it the acid reacting with water as the base to produce hydronium in the conjugate base. So what type of acid would A be showing? Yeah, you're right, strong acid. Okay, start out with just start with the acid. After it completely ionizes, there's no strong acid, HA left, and we just have ions. We just have product, H+ and A-, strong acid. Complete ionization. What about the next 2 situations? Yeah, both of these are weak acids. They only partially ionize. Okay? So most of it stays as the acid. We do get some product, some ions. Okay, that's what we call partial ionization. We do produce some ions. So what's the difference between B and C? Yeah, it's the strength of the weak acid. Okay, so this is going to seem odd. We would say this weak acid is stronger than this one down here. This would be the bottom one would be the weaker weak acid of the two, and the top one would be the stronger. This one ionizes a little bit more than the one in C. So the one in B is a stronger weak acid, sounds kind of odd, than the one in C. It's about the percent ionization would determine acid strength. And here's another way to look at it. Sometimes, molecular models are good. Here is our strong acid, HCl. Here is a weak acid, HF. Make sure you know your 6 strong acids. And what you're seeing again is complete ionization. We see, and they actually did it right here, hydronium, H3O+. Okay, so there's a bunch of hydroniums around here if you look around. I don't know if I got them all. There's another one there. And then these kind of orangish guys are the chlorides. Okay, so what you're supposed to see looking at that strong acid is that we don't have any HCl. We just have hydronium, H3O+, and Cl-. Complete ionization. Whereas for the weak acid, most of it stays as HF. Here's our HF here. Okay, most of it stays as HF. We only get a small amount of ions. Here's a hydronium. And here is a fluoride. Okay, so most of it stays as the weak acid. Partial ionization, a small amount of ions in solution. Okay, strong acid, weak acid. Make sure you know the difference. Now, for our generic weak acid, and I should write aqueous and liquids, so that we include aqueous, we do not include pure liquids. Okay, so there is our, you're going to see that these look the same. Acid in water donates an H+, producing hydronium. There's our equilibrium constant expression, also called the acid ionization constant expression. Okay, same thing. Now again, I want to remind you that it's better to think about this reaction, or also to think about it, because we're going to talk about a definition at the end of the chapter where we talk about electron donating and electron accepting, and that's a better way to think of these. So we have the, let me get a red. We should use red for this, red arrow. Okay, the electron pair from oxygen grabbing the H+, and then that electron pair kicking up onto the anion, and then we produce H3O+. We get the same products. So when water grabs this hydrogen ion, get H3O+, and then because this pair of electrons here, this bond, kicks up onto the anion, or onto A, it will now have a negative charge. Okay, so chemical reactions involve electrons. Protons just don't magically leap from one thing to the next. It has to be an attractive force with electrons pulling that hydrogen away from the anion, the A of that HA. All right, make sure you're aware you're going to have to look up Ka values sometimes. You can look up in the book, table 15.5, okay? And then in my notes, I have a different table from a different book just to show you they will look slightly different. Sapling, you can look them up there in the Chempendix, so make sure you know how to look those up. And so here's a table from another book with a certain number of acids. You will notice that the Ka values differ. Here's one, some at 10 to the negative 4th, 10 to the negative 5th, 10 to the negative 10th even. That's a really weak acid. The smaller that Ka value, the weaker the acid, the less it ionizes. Okay, so let's look at a problem. And I don't have my book with me here at home, but I think you should take a look at examples, if I remember right, 15.7 and 15.8 in the textbook if you want more practice with weak acid problems. But this is a problem we started in class. So we have the weak acid, it's a carboxylic acid, donating an H+, producing hydronium in the conjugate base. We start, 0.338 molar was a concentration given. Initial concentration of products would be 0. You get a different color pen. Now, no product, so it has to go to the right. So minus X, plus X, and plus X. And there's our equilibrium amounts. So that ice table should look pretty darn familiar to you. And these ice tables for weak acids are easier because all our coefficients are 1. Easier than the ones we worked in the last chapter. All right. We write our Ka expression. We do not include water as a pure liquid in that expression. We then plug in. Ka value would be given in the problem, or you'd have to look it up. Plug in our X and X for X squared in the numerator, products over reactants, 0.338 minus X. Now, most times you can make the assumption that the initial concentration stays about the initial Weak acids only ionize to a small amount. And so this X is going to be very small, hopefully, and we'll check that when we're done. Very small, so that 0.338 minus a really small number stays about 0.338. So that simplifies our calculation. Cross multiply 0.338 times 6.5 times 10 to the negative fifth. Get x squared is equal to 2.2 times 10 to the negative fifth. Take the square root, get your x value. In our table, let me scroll back up. Since it's an acid, acids produce hydronium. So X in that table is the hydronium ion. We now have that. Oh gosh, I knew I couldn't get through a pre-lecture without that happening. Somehow I always swipe the thumb reader on my laptop. I'm not sure how that happens. All right, so then we take this hydronium concentration, plug it in, and we get a pH of 2.33. In class, we'll compare that to what we got for the strong acid and talk about the difference in pH units. We'll save that for class, though. All right. So you will definitely see in the pre-lecture quiz problems calculating the pH, or at least one problem calculating the pH of a weak acid. If you think you need more help with that, look at the example problems in the textbook. Okay. Now, let's check our work. Let's check the 5% rule. All right. So change divided by initial, multiply by 100 to get a percentage. So what we want to find out is that change small compared to what we start with? Because that was our assumption, that that change was really small compared to the initial, and it needs to be less than 5%. And so what was our change? Our change is x in this case, and here is our x value right there. So in this case, so your change, depending on the stoichiometry, depending on the coefficient, we've done some problems in class where it was 2x. This one is just x, so we plug in our x value, 4.69 times 10 to the negative third molar. Our initial concentration, 0.338 molar. That gives us a fraction, part divided by the whole. We multiply by 100 to get a percentage. Oh, I hit something wrong on my calculator. I'm trying to go too fast here because I'm at home and dinner is pretty much ready and I'm trying to get this done. Okay, 100 times. So I get 1.39%. Hopefully I did that right. Okay? Is our assumption valid? Yes, this is less than 5%. So not much of that weak acid ionized. And we would also call this amount the percent ionization. And you might see that in the homework this week. Calculate the percent ionization. In effect, checking your 5% rule is calculating your percent ionization. Now you remember, I would say a typical weak acid only ionizes about 1%. What do you see for this weak acid? About 1.4%. Now again, that will vary. Some weak acids are stronger than others, meaning they will ionize more. When you change the concentration of a weak acid, the percent ionization changes. We'll talk about that in class as well. Okay, weak acids. Practice some of those. You'll see that in the pre-lecture quiz. Let's look and see how weak bases are different in terms of the calculation. Weak bases are a type of compound called an amine. You can also pronounce that amine. And ammonia is kind of the quintessential example. Okay? So what is it about ammonia that makes it a base? And if you remember Lewis structures, we draw out the Lewis structure for ammonia. Nitrogen has 5 valence electrons. We have 3 hydrogens, each with 1. That gives us 8 electrons. We have placed 6 in those 3 single bonds. Single bond is a 2-electron bond. We have 2 more electrons to place. Those are placed as a lone pair. Okay? So, a base in terms of the Bronsted definition is a hydrogen ion acceptor. That lone pair can accept an H+. All right. We could also think of it like water in the previous example, that nitrogen donates that electron pair and grabs that H+. Okay, that's a better way to think about it. But the Bronsted definition, base is a hydrogen ion acceptor. Now, I'm not going to spend too much time on this, but other bases are also amines, and their common distinguishing feature is a nitrogen with 3 things bonded to it with a lone pair. We need that lone pair on nitrogen to donate to that H+. So let's just look at one more, methylamine. Two of the groups are hydrogens, just like ammonia, but the other group, let me put the hydrogen up here, and then I'm going to put the methyl group down here just so I can show that it's bonded to carbon. That single bond is to carbon. So again, three single bonds, lone pair. Okay, so two hydrogens of methyl, and we can put various different groups attached to that nitrogen and have different amines. Urea, you're probably familiar with, actually has two nitrogens. Oops, sorry, I missed that nitrogen, with lone pairs. Okay? Weak bases like weak acids. Equilibrium lies far to the left. Again, typically about 1% ionization, approximate. But now, Bronsted definition, lone pair on nitrogen, accepts the H+, so ammonia is our base, hydrogen ion acceptor. Water is now functioning as an acid. So depending on what we dissolve in the water, sometimes water functions as an acid, sometimes it functions as a base, depending on what we dissolve in it. Okay? And when ammonia accepts an H+, we produce its conjugate acid. It has one more H+ than the base part of that pair. But more importantly, look at what we produce. Bases produce hydroxide. Okay, so when you're writing out these reactions, make sure that the base accepts an H+ from water, producing its conjugate acid, but more importantly, bases produce hydroxide. Acids produce hydronium, H3O+. Bases produce hydroxide. All right? Keep that in mind. It'll help you write these reactions. Practice writing these reactions. Many times students get hung up and miss points on quizzes and exams because they can't write the reaction correctly. And if you can't write it correctly, you can't set up your ice table. We can write a Kb expression for that reaction just like a Ka. We do use Kb for base. And again, you can look up these values. And here's a different table than your book showing some Kb values. So we're going to do a problem really quickly with that weak base. That weak base is aniline. And I'm going to show, there's its Kb value, 3.8 times 10 to the negative 10th. And look at the structure. And I'm going to scroll down. I have the structure drawn again down here. We have that feature, right, where we have nitrogen with 3, and I should just color those in, 3, come back, single bonds. Okay, so that's only 6 electrons. So it will have a lone pair which can accept an H+. That is a base. That's an amine. Okay? If you're wondering about this, when you go on to organic chemistry, you will see that a lot. That is a phenyl group. Okay, C6H5. So we can write that. That is C6H5, and then we have NH2 right there. That is a hydrogen ion acceptor. That is the base. We produce the conjugate acid. And more importantly, look at what we produce. Bases produce hydroxide. Say it over and over again until it's stuck somewhere. Acids produce hydronium. Bases produce hydroxide. Initial. I kept the same concentration. We could change it. Doesn't matter. Oh, I did it again! I'm just driving myself crazy. I'm trying to go too fast. Sorry. No product has to go to products. And at equilibrium, 0.338 minus x, x, and x. Does that look familiar or what? Same thing. Now, keep in mind the big difference in bases produce hydroxide. When we solve for x, we don't have hydronium, we have hydroxide. Very important. Common mistake, again, by students. We write out our Kb, products over reactants. Okay? Don't include water. Pure liquid. Kb value is really small. Okay, x times x, x squared, 0.338 minus x. What assumption are we going to make? Yes, that this is approximately x squared over 0.338. Okay, so that initial is not going to change much. We're going to assume it stays the same. Cross multiply to get x squared. So we get 1.28 times 10 to the negative 10th. Take the square root to solve for x. Okay, what is that? Well, first of all, unit, don't forget your units, is molarity. And what does that equal? X equals hydroxide. All right, so we want to calculate the pH of this solution. We have hydroxide. What do we need to calculate pH? We need hydronium. So one way you can work this, and students don't like this as much, but don't forget this equation. And I would recommend when you're practicing these to do these both ways. I'm going to show you two methods. We have hydroxide. We know Kw will focus 25 Celsius. Kw is 1 times 10 to the negative 14th. So we know Kw, we know hydroxide. Solve for hydronium. Once you get that, plug it into your pH equation. Okay, and there you go, not so bad. So we have one extra step compared to weak acid. We have to get from hydroxide to hydronium before we can calculate the pH. Now let me show you the second method. Students tend to prefer this method. We can calculate pOH. Okay, so take your hydroxide concentration, take the negative log of that, and we're going to get 4.95. That's not pH because we used hydroxide, it's pOH. Now, we can take this equation and take the log, the negative log actually, of both sides of that equation, and we'll get a new equation that looks like this. Okay, so this equation, pH plus pOH equals 14, comes directly from the Kw equation. So 10 to the negative 14th, that's where the 14 comes from. So if we know, in this case, pOH, the pH is just 14 minus the pOH. Okay, bring pOH to the other side, and we get a pH of 9.05. Is that what you expect? Is it basic? Yeah, it's greater than 7, so this is basic. That was a weak base. It produced hydroxide. Now it's a pretty darn weak base, so our pH isn't that high. We're going to do some strong base calculations where you have pHs 13, 14, or greater, potentially. Okay, so this is a weak base. We expect a pH 9 to 10, typically, maybe 9 to 11 for a weak base. Okay, last thing, I'm not going to do it. I'm going to leave that to you. This is a really, really weak base. And I want you to, one, you should check the 5% rule to make sure your assumption is valid. With 10 to the negative 10th, we're pretty much guaranteed it's going to be valid. But do this calculation anyway to see what the percent ionization is of this weak base. It's a really weak base, so the percent ionization is really small. So remember, I said that typically it's about 1%. This one is much less than 1%. So a weak base, weak acid, we're kind of looking at about 1% ionization. This one's really small. Calculate it and find out. Okay. Now, I don't have my book. There are a couple of example problems in this section on weak bases that you come to pretty early on, where you calculate the hydroxide and the pH of a weak base. If you're unclear on these, work those example problems in the text. I don't know what the numbers are because I don't have a book in front of me. Okay. Thanks for hanging with me. Sorry to get this posted late. I was really frustrated when I got all the way to the end and realized the audio cut out partway through. Not good. So anyway, I will see you in class on Friday. I'm going to post a short pre-lecture quiz and sapling for you to work based on this pre-lecture. Okay, see you soon. Take care.